Okay, so in this video, we're going to take a look at time dilation and length contraction. So this follows on from my video on introduction to special relativity. So if you haven't checked that out, I would watch that first, because this is designed to follow on from that. Because what we saw in the previous video is that a person in let's highlight that, in the reference frame of an event. So in the last video, the event we looked at was somebody shining a torch up at a mirror and it bouncing back down again. So that's the event. So someone in the reference frame of an event measures a shorter time that the light takes to travel up and come back than a person outside the reference frame. So we had a person who was standing on a platform. So what that means is if you're in the reference frame of the event, your seconds are longer. So like 1 second for you is a longer period of time than 1 second for the observer outside the reference frame. And we call that phenomenon time dilation. Okay, so that's what it really means. So what we're going to look at first of all is actually deriving an equation that allows us to know how the times are related to one another. So how much is a second longer, or how much smaller would a time measurement be if you're in the reference frame than if you're outside the reference frame. So this is the example we're going to look at again. So we've got a person on a train who is shining a torch up and down again, and they measure how long that takes to occur. And we've got this person, observer 1, who's stationary, well, outside the train or in a different reference frame, who is going to measure how long it takes to go up and down. Now, obviously, this is a thought experiment. You can't actually measure the time, but that's why this thought experiment is useful, because this isn't something you could do for real. So we said in the last one that observer 1 is going to see the light follow this diagonal style path because it's the velocity of the train would also give it a horizontal component. Observer 2 is just going to see the light go up and down. So what we're going to do is figure out the distance traveled by light in each of those two scenarios. So we're just going to look at it on the path upwards. So I'm not going to do the second half where it comes back down. So in this diagram at the bottom, we're just looking at the first half of the motion up towards the mirror. So the diagonal line of observer 1 can be expressed as the speed of light, because remember, light always travels at the same speed regardless of your reference frame, times by the time that that person would measure. So person 1 is outside the reference frame of the event, so I'm going to call that just t. Okay. Person 2 is just going to see the light go upwards. So they're going to see light travel again at the same speed, because it always does, but they're going to measure a different time, which is called t0, often known as proper time. Okay, so that's the time measured by a person inside the reference frame of the event, so the person on the train. So the difference between those two is going to be down to the velocity of the train. So that's why this green one comes from. So this is just the distance traveled by the train in the time t seconds. Now you might wonder why we pick t and not t0 along the bottom there. Well, you have to remember that the reference frame or the train is only moving from the perspective of observer 1. Remember, observer 2 doesn't think the train is moving at all. So the only time it makes sense to put in there is the person who actually thinks the train is moving. So we put in t, not t0 in there. So we've made a right-angled triangle, which means we can use some Pythagoras to get an equation relating t and t0. So let's do some calculations. So using Pythagoras, we know that ct squared is equal to vt squared plus ct0 squared. Just using Pythagoras because we've made a right-angled triangle. This is why it was important that we had the person shining the light vertically upwards and downwards, because then we've constructed this right-angled triangle. And then what we can do is obviously we can multiply out your brackets and squaring and stuff. And what I'm going to do is collect together the t terms on one side and the t0 terms on the other. So that's what I've done between the red and the black. I've just subtracted v squared t squared to the other side, and then I factorized out the t squared, and we end up with this expression here. And we're going to change it slightly, so I'm essentially going to divide the c squared through, so that's where the 1 comes from. It's c squared divided by c squared, and then b squared divided by c squared there. And then we can just square root the whole thing, and we end up with an expression. So proper time, so the time measured by the person on the train in our example, is going to be equal to the time measured by the observer outside the reference frame multiplied by this square root of 1 minus v squared over c squared. We could have written v over c all squared if we wanted, but it doesn't really make any difference. So we've got an equation that relates the two measurements of time. What we can see from this equation is that as the object's speed increases, so that's essentially what that means in here is that as v is going upwards, the proper time decreases relative to the observer outside the reference frame. So essentially this v squared over c squared term is becoming bigger, but always less than 1, because v has to be always less than c. So 1 minus a number that's getting bigger is going to be getting smaller. So the square root, as v gets bigger, gets smaller. So therefore t gets multiplied by a smaller and smaller number that is definitely less than 1, and therefore t0 is less than t and becomes increasingly less than t the bigger v is. Now, you could definitely argue it the other way. So you could be arguing that the time measured by the observer outside of the reference frame is getting bigger compared to proper time. But you have to remember that there's no absolute time. One of those observers is not correct and the other one wrong. Both of those times are correct. It just depends on your perspective. So you could definitely argue that as well. But seeing as there's no proper time, both statements are just saying the same thing. So it doesn't really matter which of the two you say, as long as you make a statement relative to another scenario there. Okay, so that's time dilation. If the speed of light is a constant, so both observers have to measure the same speed of light, if time changes, it stands to reason that lengths must also change. So what we can do is write two expressions for the speed of light. This one is the speed of light for the person outside of the reference frame of the event. And then this bottom one is the speed of light for the person inside the reference frame of the event. And they will measure distances called the proper length, which is L0. So that's just the length measured if you're in the same reference frame as the event, in this case, the light shining up and down. So what you can see from here is that the faster an object travels, the shorter the proper length becomes relative to the length measured by an observer outside of the reference frame. And we always need that comparison. We can't just say the length they're measuring is getting shorter. That is meaningless. It's the length is shorter compared to an observer outside of the reference frame. They're always relative to one another. This is why it's all called relativity. Okay, so what we can do is generate an expression linking L and L0. So the first thing I'm going to do is I made a substitution in here. So what I've done is I've replaced T0 with the equation that we just came up with for the proper time. Okay, so I've replaced it with T minus all of that stuff. And we know that that is equal to L over T, because the speed of light has to be the same for both observers. So then if you do things like you cancel out the t's and do some rearranging, we get an expression for the proper length, or the length inside the reference frame of the event, and we can relate it to the length measured by someone outside the reference frame of the event. And it's this same factor that we've seen in here, the 1 minus b squared over c squared all square rooted. Okay, so that's our equation relating the two length measurements that you could get depending on where you are as an observer. I think a valid question is going, okay, so do all of the lengths change? Or does one length change? Which one is it if so? So the only length that changes is the one parallel to the object's velocity. So the one, in our example, it's going to be the one parallel to the motion of the train. So if I just sketch the diagrams again, so remember observer 1 sees this, observer 2 sees this. So you can see this length along the bottom is the one that's changed, and that was the length that was parallel, because remember our train was going on this way. So it's this length at the bottom that has changed. It's only the one parallel to the object's velocity that is affected. The other two are completely unaffected. So A question might be, do lengths and times change for both observers? So I think I want to boil this down to one thing. So the way I think about this is that if you're an observer traveling in the reference frame of the moving object, lengths will contract from your perspective and seconds will get longer, or time measurements will get smaller. And you can see the important thing I have to add in here, compared to an observer outside the reference frame. And I'm going to keep saying this because it's really important part to get in there. It's always one changes with respect to the other one. Like, just saying one of these things changes is meaningless. In science fiction, you might have seen that if you get on a really fast spaceship, you can go forwards in time. Does that bear out when we start considering special relativity? Well, thinking about it, so if you are traveling fast relative to Earth, so you are essentially in a very fast moving rocket, what that means is your seconds are now longer than the seconds of a person who's been left on Earth. Okay, and what that means is, let's say from your perspective, you travel for 10 years. That means on Earth, more than 10 years would have passed because their seconds are shorter. So maybe they've had 15 years on Earth, or maybe they've had 20. It depends how fast you're traveling. So when you return, you would biologically have aged by 10 years. Whereas on Earth, 20 years will have passed. So I think they all think you're 20 years older. So you're 20 years will have passed on Earth. So in theory, you've essentially sort of gone forward in time, at least compared to where you would have been if you'd stayed on Earth. Okay, so there is some truth in it, but I think science fiction rather extrapolates that quite a lot. Okay, so some notation that is used to simplify some of the equations is this Lorentz or gamma factor. So essentially, the Lorentz or gamma factor is 1 over the square root of 1 minus v squared over c squared. So it's used to put into the equations to simplify them quite a bit. So essentially, we get these expressions here. So the Lorentz factor for low speeds is pretty much 1. So that's why if the speed isn't very much, we don't notice this length contraction or time dilation. As you increase towards the speed of light, this gamma factor tends towards infinity. So you can see that as this gamma factor gets bigger, the proper time is becoming smaller relative to the time for someone outside the reference frame. And it's the same thing for length as well. So that's just some notation that's used, and I'll refer to that in a little bit later on. So we've conducted everything so far with thought experiments. We've assumed the speed of light is the same for all objects. We've assumed that the laws of physics are the same in all reference frames. But we now need to get to a point where actually we do a test for it. Where does special relativity give us better predictions than what we previously thought? Because if it doesn't do that, there's no point in all of this thought experiments and stuff. So there is a scenario where special relativity makes accurate predictions, where not using special relativity doesn't. So that's how we evolved this idea and why we've kept it. And it's to do with muon decay in the Earth's atmosphere. So before special relativity, there's a long-standing problem. Essentially, too many muons are being detected on the surface of the Earth than they thought that they should be. So these muons are being formed about 10 kilometers above the Earth's surface, and they're being formed by cosmic rays producing particles. So cosmic rays are very high energy photons, so they're can very easily produce fairly big particles. So that's where the muons are coming from, and we've seen from our measurements that they're being made about 10 kilometers above the Earth's surface. So using length contraction or time dilation, we can explain why too many muons are arriving at the surface, or essentially explain why muons are traveling further or lasting longer than previous theory predicted that they would. And this is why special relativity is important, because it makes more accurate predictions. A muon is a fairly unstable particle. So just like when we met radioactivity before, where we looked at alpha, beta decay, etc., muons undergo decay as well. And if memory serves me correctly, they usually decay into electrons and some neutrinos, but that's not particularly important here. The important thing is that the decay has a half-life of about 1.56 microseconds. So let's imagine that we've produced a load of muons, and we know how many we've produced because we can measure it. After 1.56 microseconds, there would be half the number of muons than there were originally, because half of them have now turned into electrons and neutrinos and they're not there anymore. So cosmic muons travel very close to the speed of light. So they have a Lorentz factor at 190, and you can work out how fast they're traveling if you like. But essentially, it's very, very close to the speed of light. So close, in fact, we're not going to bother distinguishing very much later on. So without relativity, first of all, we'd expect the number of muons to halve every 468 meters that they travel. Where's that come from? Well, these muons are traveling at pretty much the speed of light, just under in reality, but so close that it's not worth thinking about, especially given the uncertainty of all other measurements. So that 468 has come from the speed of light times by the half-life. That's where 468's come from. So after 4,700 meters, or 10 times the distance, the number of muons would have halved 10 times, and so it would be less than 0.1% of what it was originally. So that's what conventional theory, if you like, predicts. And this is why we have this too many muons problem, because we have far in excess of 0.1% of what we originally had. I think if memory serves, you end up with just under half or something like that. Okay, so that's the problem. Now think of this from the perspective of the muon and use special relativity and our Lorentz factor. So remember, from the muon's perspective, it's the thing moving. So let's say I'm an observer and I'm moving with the muons. To me, lengths are contracted. Okay, and they're contracted by the Lorentz factor, so they're contracted by 190. So the distance I said that they were formed from the Earth's surface was 10 kilometers. But actually, to me, that isn't 10 kilometers. It's 10 kilometers divided by 190, so it's considerably smaller. So the muon still has a half distance of 468 meters, if you like. So that means that, let's say, I don't know, for simplicity, let's say we're going to divide by 200. So that, from the muon's perspective, let's see if I can do 10,000 divided by 200. That sounds like 50 to me. Is that right? That'll be 2000, 10,000. Yeah. So essentially, from the muon's perspective, the distance they are formed above the Earth's surface is actually about 50 meters using this gamma factor. So that means that most of them, in fact, would make it to the Earth's surface. Because they haven't even traveled one half distance, or they'll have reached the surface before even one half-life has occurred. Actually, they could travel 88,900 meters before even their number would have even halved. Okay, so loads of them will make it to the surface. In fact, the majority of them are going to make it to the surface. So that's viewing it from the perspective of the muon. Okay, so what does this look like from an observer on the Earth, so outside of the reference frame of the muon? So remember, from the muon's perspective, time is dilated compared to an observer on the Earth. So to us, looking at it, it appears that the half-life is 190 times bigger, because the muon's seconds are 190 times bigger, effectively. So to us, it seems like their half-life is too big compared to when we're just measuring with muons in a laboratory. So that's how it looks like. That's what it looks like to us as observers on Earth. It looks to us like their half-life is much bigger, which is why, given their speed, they end up traveling much further. So that's what it appears like to us. Final thought to leave you with. Anyone who's been on the internet will know there's lots of flat earthers out there with lots of fun theories of that. Does special relativity give us some justification for flat earth theory? Well, first off, no, it doesn't. But second off, if you were an observer in the reference frame of a photon traveling towards Earth, that would mean lengths would contract to zero. So the thickness of Earth parallel to your speed would technically be tending towards zero. So if you were an observer from the perspective of a moving photon, yes, the Earth would have a thickness of zero and technically be flat. However, you as an observer are not physically able to travel at the speed of light, so consequently, it's not flat, and flat Earth nonsense is absolute rubbish.